In this problem, we are working on finding the solution of the given initial value problem. Then we want to plot a graph of the solution. So here we can see that our equation is the third derivative of y plus the first 4 times the first derivative of y is equal to t, where y of 0 is equal to y prime of 0, which is equal to 0, and y double prime of 0 is equal to 1. Let's get started. First we have the characteristic equation, which is solving the homogeneous component. We have r cubed plus 4r is equal to 0. We can factor out the r, and our result is that we get r is equal to 0 and r squared is equal to negative 4. Now when we take the square root of this, we realize that we have two imaginary components, the positive and the negative 2i. As such, our general solution equation looks like this. We have 1, which is y is equal to e to the negative 4t, and we have two others. One which is y is equal to cosine of 2t, and another which is y is equal to sine of 2t. Now we need to find our particular solution, which is the solution of the non-homogeneous equation. We are going to do this using the method of undetermined coefficients. Starting out, we are going to start off with capital Y of t, which is going to denote the non-homogeneous solution, is equal to at squared plus bt plus c. Here we are using a second-degree polynomial because our g of t solution, which in this case is t, is a first-degree polynomial, and we want to make sure that we are capturing any possible value in our solution. Here we have our characteristic equation, y of t is equal to at squared plus bt plus c. Now when we take our first derivative, we end up with 2 times at plus b. When we take our second derivative, we end up with just 2a. And finally, when we take our third derivative, we end up with 0. Plugging this into our characteristic equation, we have the third derivative of y plus the 4 times the first derivative of y is equal to t. This becomes 0 plus 4 times 2a times t plus b, which is equal to t. Therefore, we have 8a times t plus 4b is equal to t plus 0. As you can see, we have a component that is being multiplied by the t, and we also have a singular constant value. As such, we can break up the equation into two parts and set them equal to each other. Here we have 8a is equal to 1 because those are the coefficients of the t values, and 4b is equal to 0 because those are the values of the constants. As such, we find that a is equal to 1/8 and b is equal to 0. We do not have a c in this equation, so c must not exist. Finally, we get that our general solution is y is equal to c1 times e to the negative 4t plus c2 times cosine of 2t plus c3 times sine of 2t plus 1/8 t squared. Our initial conditions are y of 0 is equal to, here we have c1 plus c2, and that is going to be equal to 0. Next we have y prime of 0, which first we're taking the derivative of y, which as you can see has already been filled in. So we have negative 4c1 times e to the 0th power, e to the 0th power is equal to 1, minus 2 times c2 sine of 2, which is equal to 0, plus 2c3 cosine of 0, which is equal to 1, plus, again, we have a t component, so that is multiplied by 0 and equals to 0. Finally, we plug in our formula and values for the second derivative of y. We end up with y double prime of 0 is equal to 16 times c1 minus 4 times c2 minus 4 times c3 plus 1/4. However, the 4 times c3 component is being multiplied by sine of 0, which is equal to 0. As you can see on the right-hand side, we have our resulting equations. We know that c1 plus c2 must be equal to 0. Negative 4c1 plus 2c3 is also equal to 0, and 16c1 minus 4c2 plus 1/4 is equal to 1. Solving this system of equations, we get that c1 is equal to 3 divided by 80, c2 is equal to negative 3/80ths, and c3 is equal to 3/40ths. Therefore, we have our final solution, which is y is equal to 3/80ths e to the negative 4t minus 3/80ths cosine of 2t plus 3/40ths sine of 2t plus 1/8 t squared. Here we have our graph of this solution. As you can see that when t is less than 0, the function acts similar to an exponential function. As t is greater than 0, the function holds a slight oscillation as part of the cosine and sine functions, which are a part of our equation. But generally, we see that our graph follows the general parabolic shape. This is because of our t squared component. Moving on, we are next going to do the second part. For this problem, our goal is to find the general solution of the given differential equation. However, we may leave some of our answer in one or more integrals. Our equation is the third derivative of y minus the second derivative of y plus the first derivative of y minus y is equal to secant of t. First, we need to solve the characteristic equation. The characteristic equation is r cubed minus r squared plus r minus 1, which is equal to 0. We are going to use the grouping method. So first we are factoring out r squared from r cubed minus r squared, which leaves r minus 1. Next, we are factoring out the positive 1 from r minus 1, which is equal to 0. This leaves us with the common factor of r minus 1, and now we have r squared plus 1 times r minus 1 must be equal to 0. Using the zero product property, we get that r is equal to 1 and r squared is equal to plus or minus I. This means that our characteristic equation for the homogeneous component of this solution is going to be y1 is equal to e to the negative t, y2 is equal to cosine of t, and y3 is equal to sine of t. Moving on, we are going to use the variation of parameters to find the non-homogeneous component. First, we're going to take the Wronskian of y1, y2, and y3. The Wronskian is the determinant of a 3x3 matrix formed by the top row, which is each of our equations, and the second row, which is the first derivative of each of our equations, and the third row, which is the second derivative of each of our equations. Here we are using a fun shortcut method, and I'm not going to go into details about it in this video, but it is solved out for you if you would like to see that. But basically, that's a long way of how we got the solution, which is 2e to the negative t. Next, we need to find the Wronskians of each individual equation. We do this by setting that column equal to 0, 0, and 1. For example, for the first Wronskian, we have 0, 0, 1 as the first column, and then we have our cosine column and our sine column. Whereas for the second Wronskian, we have our first column as e to the negative t, our second column as the 0, 0, 1, and our third column as the sine column. As you can see, the first Wronskian is equal to 1. The second Wronskian is equal to negative e to the negative t times cosine t plus sine t. Our third Wronskian is e to the negative t times cosine of t plus sine of t. Now we need to plug it into the general solution equation for the particular part. This is the non-homogeneous component. Here we have capital Y of t is equal to the summation from m is equal to 1 to n of y subscript m, which represents our equation, times the integral from t naught to t of g of s, where g of s is the non-homogeneous part of the solution. So in this case, it is secant of t, times the Wronskian of the individual equation, which is represented as W subscript m, divided by the Wronskian of all three equations, times ds. Breaking this up into bit by bit, here we have capital Y of t is equal to y1 times the integral from t0 to t of secant of t times 1 divided by 2e to the negative t, where 2e to the negative t is the Wronskian, 1 is the first Wronskian, and secant of t is equal to g. Here we have the second, which is adding to it y2 times the integral from t0 to t of secant of t times negative e to the negative t times cosine of t plus sine of t divided by 2e to the negative t dt, plus the third, which is going to be y3 times the integral from t0 to t of secant t times e to the negative t times cosine of t plus sine of t divided by 2e to the negative t dt. This is equal to e to the negative t times the integral from t0 to t of secant of t 2e to the negative t dt. Here we have simply removed the times 1 as that is redundant. These next few, however, we have simplified by canceling out the e to the negative t. So, for example, we have plus cosine of t times the integral from t0 to t of secant t times cosine of t plus sine of t divided by negative 2 dt plus sine of t times the integral from t0 to t of secant times cosine of t minus sine of t divided by 2. This is our final solution, as we are able to leave our solution in terms of the integrals. It's important to remember that we have secant of t is actually equal to 1 divided by cosine of t. This is important if you would be solving these integrals by hand. However, that is beyond the scope of this video. Thank you so much for watching, and have a good day.